Hello everyone. In this tutorial we are going to describe how can you model a reinforced concrete beam in ABAQUS, how to model the reinforcement, how to assemble the main reinforcement, the stirrups, and how to apply the load. So we are going to go through this example over here. So this is a 4-point bending example. This is just a generic beam that we see over here. We are going to draw a 3D model. In our case, this is a 3-meter beam, or if you consider the length between the supports, so 2.6 meter, and then you have two loads applied here with a spacing of 800 millimeter. So we are going to apply displacement control here, and we have the reinforcement. We have 3 phi 20 bars for tensile reinforcement, 2 phi 10 for compression reinforcement, and we have some stirrups, phi 10 stirrups, 2 legs at 200 millimeter spacing, and the beam itself is 200 by 500. And over here we can see the dimensions of the different bars, reinforcement bars. Again, this is just a generic beam, just for the sake of illustrating how to do this type of modeling in ABAQUS. Just a quick note before we start. So here, as you see, of course, this we are going to model this, as I mentioned, in 3D. And again, this beam is symmetric. So if you want to be efficient, of course, the proper way or the smart way would be to make use of this symmetry and perhaps just model half of the beam, and then this will make it, of course, much faster when you run the analysis and everything. But for the sake of simplicity, for this tutorial, we are going to model the entire thing. We are not going to make use of the symmetry, but just make note that actually you can do that in order to make your model simpler and faster. All right, so let's go to ABAQUS and start modeling our problem. All right, so now we have ABAQUS open, and the first thing that we are going to start is by starting drawing the different parts. So I'll go ahead and start creating the beam part. So click here, I will call this beam, and this is a 3D part, deformable, solid. And here I'm going to use an approximate size of 500 so that the sketch would fit my beam cross section. I'm going to say continue. So over here, the beam cross section, it's a rectangular cross section. So we just need to draw this over here. So from -100 all the way to this point at the top. So here we have our cross section. Let's put dimensions just to demonstrate the dimensions over here. So 200 by 500, and that's it. And then I can click done, and then we are going to extrude for 3-meter long beam, and then we are going to click OK. Before we move to the other parts, let me start by doing some partitions. And for doing the partitions, we'll first start by doing some perhaps datum planes. So I'm going to create a datum plane parallel to the XY axis, and I want a datum plane at 100 millimeter. So this will be the datum plane over here. So this will help me later on, once I do the partition here. This will help me when I'm trying to place my supports during the assembly portion of our modeling. So again, we're going to do another one over here. So this will be 2900, so 100 millimeter from this end. I'm going to do other two planes as well over here. So this is where the supports for the 4-point loading will be located. So I will have one at 1100 from this point, and again I will have another one. So this will be 3000 minus 1100. So that would be 1900. So here we go, that's all right. So that's it. Now we have our datum planes, then we can start doing the partitions. So if I click on this icon over here and then we select partition cell using datum plane, and then we just need to start selecting the datum plane. So now we have our first partition. Then I'm going to select this cell and then I'm going to select this datum plane, and then I create a partition, the same thing again, create a partition, and then this last cell, and then this datum plane, and create a partition. So now I have a partition, so it will be easy to place again our supports at the end. Let's create another part. So the next part that we can do is the support. So here I'm going to create a new part. I will call it supports. So this will be pretty much the supports as well as the parts that we are going to load the beam. So for this we are going to draw half a cylinder, pretty much similar to the problem statement. So similar to what we see over here. So we are going to create like half a cylinder so that we apply the displacement or we apply the supports. There are many ways to do this actually, like perhaps the most ideal way is to use an analytical rigid or a discrete rigid part type when you create these supports. But for simplicity here, I just will make it a solid part, typical solid part, and then we'll need to mesh it and we'll need to assign it some kind of material. Typically this is a steel support, so I'm going to assign it like an elastic material. But the more appropriate way would be to actually use analytical rigid or discrete rigid if you don't want to make sure that you don't have any deformations or in these rigid pieces. So we'll go ahead with that. For the approximate size, I'm going to make it 200. I'm going to say continue. So here I'm just going to create my piece. So I'm going to create half over here. So I can create an entire circle. So with a diameter of 200 millimeter. And then we can create a line from this point to this point. And then we can trim this part over here. That's it. So now we have half a cylinder. And then we can click on done. And then I'm going to extrude this 200 millimeter out of plane as well. So right now I have my support. Okay, so now we have these parts. I don't need to do any partitions over here. This is fine. Then we need to create the new parts for the stirrups and for the main reinforcement. So I'm going to create a part. This one I will call it stirrup. And this will be again 3D deformable. And we are going to select wire. So this, we are going to draw this. This is a wire element. Again, I'm going to use the approximate size 500. Again, I'm going to say continue. So again, this is the stirrup. It's a pretty much a rectangular section, 160 by 450. So let's draw that. Again, when I'm trying to draw, I always try to draw with the origin point like concentric to my sketch. So I'm going to go here -80. So -80, and we said 450. So -80 and 225, yes, so this point over here, and then all the way to 80. The other corner would be 80 and 225. Well, I can perhaps write it much easier, but yeah, here you go. So this point over here, so let me put the dimensions just for reference. So 160, and over here 450. All right, so these are the dimensions. Perhaps as well, since to be more realistic, perhaps we want to put like some fillet at the corners. So I'm going to do that. I'm going to create a fillet. The radius of this fillet, I'm going to use a 10 millimeter radius. So I'm going to select this corner, this corner and the last one. So now that's it. I'm going to select done. Well, there is no extrusion here. So right now I have my stirrup. Again, this is a wire part that will need to be assigned, of course, some kind of cross section and a material. All right. So let's create another part. So this is for the main reinforcement, the tensile rebar, pretty much. So let's create the tensile rebar, deformable wire again. And here the dimensions, that's fine. Let's keep it 500. Let's say okay. So let's remind ourselves what is the dimension. So this is 2850 by 300. All right, so let's draw that. So we can draw again like this. So we have 2000. So we can go from negative 2850. So that's 1000. Half of it would be 25. And we can say negative 300. So that's the first point, and the second point will be 1425 with 30. Okay, so if I zoom out, so here you go, and then of course I need to delete this part over here. All right, so now I have my main rebar. Again, I will need to put like some fillet at the end. So this is the mandrel diameter, pretty much when you bend this bar. So I'm going to say maybe 20, radius of 20 millimeter, or maybe 15. Let's see. Okay, so that seems all right. Maybe a little bit small. Maybe you can modify that. Let's make it 20. All right. Okay, and let's do another fillet at the other end, 20 between this, at this corner. So that's it. So now I have my main tensile rebar. Again, this is a wire element. We can create the similar thing for the other rebar, for the compression rebar. So let's create a new part. So I'm going to say this comp rebar, again wire. I'm going to say continue. I'm going to create this with using the rectangle option over here, and again let's say, so this we have negative 1425, and let me remember what was the value over here. So this is 120. Okay, so we can say over here 0, and then this can go to 1425 to 120. All right, so here we go, and then we just need to delete this part over here, and then again we need to do like some fillet at this corner and at this corner as well. So that's it, we're done. Okay, so now we have all our parts. We have done all our parts over here. So now we can go to our next step, which is defining the property. And for the property, we need some materials to be defined. Actually, I already have, I can go to my material library. So I already have this defined. So I'm going to import from my material library the concrete damage material. So I'm going to add this. I'm going to add a steel rebar, and that would be it. So that's it. I'm going to use those two, import them. So if I go here in the material, so now I have those two materials. I'm not going to go through the definition of the concrete CDP model. You can refer to the other videos that we have that go in detail how to define the concrete damage plasticity model. But anyway, so we have here all the properties defined for our concrete material, including damage. For the steel rebar, We are using here pretty much, this is typical steel, so we have Young's modulus, Poisson ratio, and for the plastic branch, we have here a yield stress of 372 and an ultimate stress of about 500 MPa. I'm going to define a new one as well. I'm going to call this steel elastic. And this one I'm going to apply here a density. I'm going to put the density of steel 7.85 e to the power negative 9. I'm going to assign the elastic branch 200,000 MPa and Poisson ratio 0.3. That's it. So this is just an elastic material that I'm going to apply to the supports pretty much, because these, well, we are not expecting them to yield anyway. So that's it. So I have my materials defined. Then I will need to create a section. So for the beam, I'm going to create section. I'm going to call it section beam. And this is a solid section, homogeneous. I'm going to assign it the concrete damage plasticity model. I'm going to say OK. I'm going to create another section, and these are the sections for for the supports. So this is, I'm going to call it section support. So this is again a solid homogeneous, and this I will assign the steel elastic material. That's it. Now I need to define the section for the rebar, and the rebars are wire elements. So wire elements, when we define the section over here, all right, we need to select the type beam. So this is, I'm going to call it section beam. Let's call this phi. So we have two diameter of bars. So we have phi 10 and we have phi 20. So I'm going to call this phi 10. And actually, I'm going to model my rebars using the truss option. So I'm going to model them as a truss, and I'm going to mesh them as a truss as well. There is another option that you can model them as a beam. If you look in literature, there are many studies that say what would be the differences if you model it as a beam or model it as a truss. In general, the differences are not that significant, but in this case over here, I find it is always simpler to use the truss option. For this example, it is fine to use the truss option. So I'm going to use truss over here, then continue. And then I need to assign a material, which is the rebar material. And of course, I need to provide the cross section area. So this is phi 10. So phi 10, if I do a computation, let's see, 10 by 10 divided by 4. So this is about 79 millimeter square. That's it. And then let's create another section as well. This is, I call it section, the section for phi 20. For the 20 diameter bar, I'm going to use the truss as well. Continue. The material is steel rebar. The cross section, let me compute how much is the area. So that would be 314. Note here that when you define a wire element section using the truss type, you provide the cross section area. That's it. But if you define it as a beam, you will need to provide the actual dimension or the actual cross-section shape. And in this case, we will need to create a profile. But since I'm using truss, I just provide the area and that's it. Now it's fully defined. So now we have all our sections defined. So now it's a matter of assigning the sections to the different parts. So right now I have the compression rebar. Let me assign the section. So I'm going to select my rebar, done. I'm going to assign this is a phi 10, all right, done. Then let's look at the stirrup as well. Let me select the entire thing. Again, this is phi 10, okay. Let me select the tensile rebar. we look like this, and then again this is the phi 20, so I'm going to select that and I'm going to assign it the phi 20 section. All right, then we have the beam. So the beam, I'm going to select the entire beam. We're going to assign this the section beam. All right, and the last thing is the support. I'm going to select this and assign it the section support. All right, so now we have the property all defined for all our parts. Then we go to the assembly. So now let's assemble our things. So let me import the beam. So the beam, here it is. I'm going to also, let's bring in the stirrup, the tensile rebar, the compression rebar, and one of the supports. All right, okay. So now we have everything over here. Let's now move things. So the first thing perhaps is to move the supports. So if you go here, so you have the support over here, so you just need to move it. So I'll select the move here. I'm going to select the support and I'm going to move this from this point to this point. So here it is. All right, and we can rotate it as well. So I'm going to select it and I'm going to rotate it around this axis 90 degrees. Oh, let me see if this is not 90 degrees. Perhaps I can do negative 90 degrees. Yes. All right, okay, so now I have it over here. We can create another one. We can import a new instance, or we can just use a pattern. So I'm going to do a pattern option, and I'm just going to select in this direction with an offset of 800. Here you go. So now we have the other one. All right, we can now do the another one over here. We can import, let's import another support as well. Okay, again, and let's move this support over here. Yes, let's move it from this point to this point. Okay, and now we'll need to rotate it as well. So okay, let's rotate this from around this axis 180 degrees. Oops, let me see here. Oh, wait a minute. Let me modify this again. So let me rotate that. Yes, done. And I'm going to rotate this. I think I did a mistake by selecting the points. So I'm going to select it, yes, from this point to this point over here, 180 degrees. All right, so now it's rotated like that. Okay, that's correct. And then I'm going to rotate it again, and this time around this axis. Let's try negative 90. Yes, that's correct. So that's it. So now I have the other support located correctly, and then I can use the pattern again to, or the mirror, or there are different options. And then in this direction, the distance is 2,600. Oh, not 2,600, sorry, 2,800. So that's it. That correct? Yes. Okay. So here you go, 2,800. So this is fine. So now we have it like this. So now the supports are there. Let's make the colors by parts so that we have some differentiation between colors. So now I need to move my rebar, all right, to the location. So how can we do that? Well, first let's look at, let's place our stirrup. So our stirrup is over here. You can see it. All right. So we have a stirrup located actually over the support. So if we look at this again here, so we have the stirrup located above the support, and then the spacing is 200 between them. So we are going to do that. So let's move our stirrup from here, and then I'm going to displace this pretty much in the Z direction, amount of 100 millimeter. So that's it. So here we go. So now we have the first stirrup done, and then we just need to make an array pretty much. So a pattern for this. So how can we move it? If we want to select this, so again, we cannot select it because now it's inside the beam. So there are different ways. One way is that you can go here to create display group. You can select, where is it? Part model instances. You can select beam and you can remove the beam, and then you can do that. So this is something that we can do. So select instance to pattern. So now I'm going to select my stirrup, and then I need to select the direction. So I'm going to select this direction, and then we need a spacing of 200, and basically we need to do this 15 times. So that's it. So that's all. So now we have all our stirrups located correctly. So now let's do the same with the main reinforcement. So I'm going to go with the tensile reinforcement. I'm going to rotate the tensile reinforcement first. So I'm going to select it, and then we want to rotate it pretty much. So how can we rotate that? Let's see. Well, let me first, actually, before I rotate it, let me move it. Let me move it from, let's see, the midpoint over here. Perhaps I can rotate a little bit so that I can see what's going on. Okay, so let me actually look this direction. Okay, so over here, so it's like that. Okay, so it's located in this direction. That's fine. We can, let me see, how can we move that? Yes, here is the midpoint. So I'm going to move this midpoint to over here first. Okay, so now I moved it, and then I can rotate it. So let me now rotate it. So I'm going to select it, and then I can rotate it from this point to this point, 90 degrees. Yes. And then we will need to center it pretty much. So let me look at this direction. So we just need to center it. So if I look in the 3D, let me now select move. I'm going to select this, done, and I'm going to move it from this point to pretty much the center, which over here, this point. Okay, so I think now if we look, yes, so now it's centered. Now if I look in the other direction, I just need to bring it a little bit up because there is some offset. So if you want to visualize this, perhaps the good way would be to go to view, assembly, display options, and if we can render the beam profiles so that we can see the actual thickness of the stirrup, because right now we're only seeing wires. I'm going to say okay. Yes, so now we can see the thickness of the wires. So now let's move the bar. I'm going to move it in the Y direction. So we need the offset of half the diameter of the stirrup, which is 5 millimeter, and half the diameter of the main bar, which is 10. So that would be 15. So if I do that, so that's it. So here is my bar inside the stirrup. That's fine. And then we can create a pattern pretty much to create the other two bars. So I'm going to do this in this direction. This would be what would be the value. Let me visualize it here. That would be 65. I think that would be correct. So 65, let me see. Yes, so this is correct. So this is exactly what I will need. And then I'm going to do the same thing again over here. Yes, dismiss. So this is again 65, but in the opposite direction. So that's it. So now I have my 3 bars now located correctly. I'm going to do the same thing for the top support, for the top, compression reinforcement. So let's first move this bar to its correct location. So let's move it first to the center and then let's rotate it. I'm going to select that. I'm going to rotate it around this axis by 90 degrees. All right. And then I'm going to center it. Same thing that we did with the tensile reinforcement. Where is the center? Let me look here so that, okay, so here it is. I think the center is over here. So from this point all the way to this point. Is that correct? No, that's not correct. So let me select it again. I think it needs to move negative 200. No, negative 200, not 20. Is that correct? Let me look here. Oh, not correct. So sorry for that. Let me, so 0, 0, and then I think that's 100. All right. Not really. I think I did a mistake at one point with the numbers. So I can just do it here by trial and error. Just missed with the values. Yeah, that seems correct. Yes, so this seems correct. That's fine. All right, and now let's move it. So we just need to move this right now. So we need to move this bar to the actual correct location. So I just want to find the center point. Yes, so this is the center point of the bar, and the center point need to be here. Okay, so that's correct. So now let's look in the other view. All right, so now we need to select this thing. We need to move it in the Y direction. We have an offset of 5 and 5, 2 diameters. So that's negative 10 in Y. So that's correct. And now we need to move it. We just have 2 bars at the top. So we need to move this in the X direction, 65 millimeter. Here we go. And then we need to do another bar. So, okay, let's use this one. And then this one will be 65 and 65. So that's 130. So here we go. So that's it. So now I have my cage, reinforcement cage, pretty much the 3 main bars, the stirrups and everything. So now I can show my beam again. And actually after I show the beam, if you want to see the inside the beam, you can click on this one. So this is to toggle the translucency or the transparency pretty much of my part. So if I click on that, so now you can see inside what's going on. You can change the amount of translucency again by moving this slider over here. So here everything seems correct. So that's good. So the location, everything is fine. So we're done with the assembly. So the next thing that I need to do is going to the step. So now I'm going to create a new step. I'm going to call this the loading step. And this would be, of course, dynamic explicit, because again, this is concrete and we have a softening branch, so we need to use a dynamic explicit analysis step. I'm going to say continue. For the time period, I'm going to say, let's say 10 seconds. That's fine, 10 seconds. I'm not going to apply lots of load, so 10 seconds I'm going to apply perhaps 20 millimeter. So 20 millimeter in 10 seconds, that's like 10 millimeter in 5 seconds. It's a little bit fast, but I think the dynamic effects will not be substantial in this case, but we could go slower, of course. I'm not doing, as you notice, no mass scaling, nothing of these sorts. Again, this is a last resort thing. You can refer to the other videos that we have on how to use an explicit analysis solver. So then I'm going to define the interaction. So I will define a general interaction property first. So let me create an interaction property. Leave the name as it is. So this is a contact for tangential behavior. So I'm going to have, this is pretty much between the supports and the beam, so steel to concrete. So I'm going to use like 0.35 friction coefficient. And for the normal behavior, I'm going to use a hard contact, and I will allow separation. That's fine after contact. It doesn't matter anyway. I don't have any separation. So this is just to simulate the contact between the steel supports and the beam. So I did the property. Now let me create a general interaction. So I'm going to do this in the initial step. So this is, I'm going to use the general contact that will apply everywhere in my model. And I'm going to select the property that I just defined over here, and that's it. Now, if you have watched our previous tutorials, we typically use reference points at the supports and at the loading points to apply the loads, which is of course the recommended way of doing things. But right now, just for to make things quicker, instead of creating reference points and creating rigid body constraints, again, you can refer to other videos regarding how to do that. Just for simplicity, I'm going to apply the boundary conditions directly on the surfaces of the supports. So before I go to load, I just have a constraint that I need to define, which is the embedment of the rebar and the surrounding concrete. So if you click over here, if you select embedded region, so I can call this embedded rebar and continue. So I need to select the embedded region, and my embedded region will be, in this case, all the reinforcement inside. So I'm going to select all the reinforcement inside. Sorry, without selecting the beam. So if I want to select just the reinforcement, I can go from here and I can select this option to select only entities that are inside the drag shape. Then let's look in this view again, and let me select again. So now I selected only the rebar. That's it. And now I need to select the host region, and I'm going to select the region. And in this case, the region would be, I need to select the beam. So I'm selecting all these cells of the beam. And then I'm going to select done. Everything I will leave as it is, the default. I'm going to say OK. So now I have the embedment of my rebar inside the concrete. Then I'm done with the interaction. The next step would be the meshing. So I'll go for the meshing. Let's go for the supports. So here for the supports, I don't really care much about the supports. So let's see the meshing. So that's, here it is. Perhaps if we use the mesh controls and use a medial axis, typically you will get better mesh structure for when you have cylinders or circular shapes. So you see here it looks better. Let's go for the beam. For the beam, let's first select the size. So for the global size, I'm going to use like 30 millimeter. And that seems fine. I'm going to say okay. For the element type, let me select the entire thing. And here, of course, we're using the explicit library. I'm going to use a linear hex, or like a brick element, pretty much. Three-dimensional brick element with 8 nodes. But I'm not going to use a reduced integration, because sometimes when you use the reduced integration, especially with concrete, you can get hourglassing modes. So I'm going to use the other option here, which is the incompatible modes. So to get like better bending behavior for my mesh elements, I'm going to say okay. Done. And then I'm going to mesh the part. So that's it, I have the mesh. Then I'm going to go to the stirrup. So the stirrup over here, again, these are truss elements. So I just need to set the global size. Let's try 20. Looks fine. Perhaps we can make it even less. Can go like 40. Yeah, that's all right. And then we can mesh it. So by default, of course, the mesh element type would be like, let me select it just for you to see it. So the mesh element type is already the linear. So this is the B31. This is the linear truss element. So that's fine. So this is the one by default. I'm going to do the same for the tensile rebar. Again, I'm going to use a size of 40. That's okay, looks fine. Mesh it, it's meshed. The same thing for the compression rebar. Let's do the same, 40. Okay, we mesh it. That's all right. So now everything has been meshed in my structure. So everything is ready to go. So that's it. The next step is to run the job. Before I do that, let me first, we didn't apply the loads yet, by the way, in the boundary conditions. So let's go to the load first before the mesh. So for the loads, let's create the fixed supports. So this is, we're going to use well, it doesn't matter, we can use the symmetry and symmetry, all right. And then for this, I'm going to select the two base supports. I'm going to select this surface and this surface. Again, ideally you would do a reference point and you apply things at the reference point, but here, just for simplicity, I'm applying things directly on the surfaces. And I'm going to do an encaster, that's fine. Or pinned, it doesn't matter in this case, to be honest. These are three-dimensional elements anyway, so you can make this pinned, it doesn't matter. And then let's create a new, the one for the load, the actual load. So this is the displacement that will be applied in the loading step. So this is the top displacement, pretty much. And I'm going to apply this over here at these two surfaces equally. And at these 2 points, I don't want to see any movement out of plane, and I don't want to see any movement in the Z direction. And in the U2 direction, I'm going to apply negative 20 millimeter vertical. So they will be applied downward, and I need to provide an amplitude for that. So let me create an amplitude. At time 0, the amplitude will be 0, so this is a monotonic, and at time 10 seconds, the amplitude will be 1. And I'm going to use this amplitude over here, and that's pretty much it. So now I will have the displacement being applied downward. So now everything is ready. Before I go to the job, let me go to the field output. Let me modify here the field output. I just don't want to save many things. So I'm going to save, I want to see output every, let's say 0.2 seconds exactly. And maybe I don't want to see any values regarding the contact. I don't want to see this field variable. I don't care about this. I just want to see the strain PE, and in this case, and I don't want this one. Reaction forces, yes, typically reaction forces. I don't want anything regarding the volume or the thickness. Let me remove here from the strains. I only want PE. That's it. So this will save me time, of course, when I run things. Forces reactions. Here I don't want to see anything regarding to velocity or acceleration. It's irrelevant in this case. So again, this is to make my model to run faster. I'm going to say OK. So that's it. Of course, again, ideally, you would put a reference point at the supports. It would make it easier after you run the analysis if you want to plot the relation between the top displacement and the reaction force. So it will be easier to extract this at a specific point, at a reference point. But if I run it like this, I will need to extract pretty much the reaction force at all points of the support base and then sum them up in order to get the final reaction, total reaction. But anyway, again, this is something that you should do. But here, just to make things faster for the sake of the tutorial, I didn't do a reference point and rigid body constraint in this case. So that's it. We are done. We just need to create the job. Okay, I'll call it job 1. It's fine. I'm going to use multiple processor to make things faster, and don't forget to here for the precision to use a double precision. So now everything is ready. I can submit. Actually, one more thing before I submit, perhaps in the load, it would be wise as well that you provide out of plane restraint to the beam, because the beam itself right now, there is nothing stopping it from moving in the X direction, so out of plane. So we can do something like out of plane constraint, right? And I can perhaps select this edge over here and this, oops, this like these two faces at the end, and I can block those from moving out of plane. All right, that's it. So this is better just to provide like because in reality, of course, you would put something to resist out of plane movement, and again, when it comes to the numerical model, the finite element analysis, this will provide more stability. So that's it. Everything is ready. Then we just need to submit. So let's submit this and let's look at the results once it's finished. All right, so analysis has been concluded, and here I load the analysis, and we can observe here the deformation. So let's see how it looks. So right now we are looking at von Mises stresses, which perhaps not very useful in this case, but we can see the deformation. Perhaps I can increase the scale factor here to make it 10, just to see the deformation more. And we can look maybe on the elastic strain, the maximum plastic strain. And as you see here, the values are showing here 0. This is because I just modify the format here just to show 1 decimal point. But if I show the entire value, you will see the value of the strain. But you can see here that at the beginning, you are getting the flexure cracks, pretty much the tensile strains in the concrete over here. And if you keep loading, now you get the 45-degree cracks that pretty much move closer to the supports. So that looks very good over here. If you want to see inside, so this is for the beam, you can look at different things, of course, different values. Let me make this a little bit smaller, 5. If you want to see inside the beam, so again, you can click on this toggle transparency, and then you can see inside what's going on. Or maybe if we want to look at the reinforcement itself, so we can go here to display group and We can remove the beam from the view, and then we have our rebars, and the rebars, again, these are truss elements. So if you want to see the forces or the stresses inside them, you just need to select on stresses, and if you click on S11, we can also go to view, ODB display options, and we can render the beam profiles just to see the thickness. So over here you can see what's going on. So you can see the values of the stresses in the bars pretty much. The compression bar at the top is in compression, of course, and the tensile bars are in tension with maximum values at the middle. So everything seems to be working fine. So that's it. This was a quick tutorial, again, how to do to model reinforced concrete in general in ABAQUS, and more specifically how to do a 4-point model for an RC beam in ABAQUS, and how to visualize the results. So that's it. Thank you, and we'll see you in another video soon.